Hello, welcome back to lesson 4.6. This is going to be all over exponential, logistic, and logarithmic models. So just kind of going back over exponential growth and exponential decay. So these are going to be the base models that we're going to use for exponential growth and exponential decay. So sometimes they're written with a base A, where A just has to be greater than 1, or decay is A is between 0 and 1. If not, there are a lot of models that we do in science and finance where we use our base E, and so we might use these formulas, but we'll let you know. So let's look at number 21 on page 387. It says, this is a chemistry problem. It says it takes 5,700 years for an initial amount of A sub 0 of carbon-14 to break down into half of the initial amount. That's called the half-life. So it says, given an initial amount of A sub 0 grams of carbon-14 at T0, find an exponential decay model that fits this model that gives the amount of carbon-14 at time T. Okay, so we're using this function similar to this one here. Okay, so we know the half-life. So similar to what we were doing in lesson 4.5, we know that when we're talking about half-life, we know that the new amount compared to the old amount is 1/2. So we can just say 1/2 is equal to our e to the kt. Okay, because we know that this ratio is 1/2. And ours is 5,700 years. 5,700 years. Wow. So this is 1/2 equals e to the 5,700 k. We're trying to find out k. So we're going to take the natural log of 1/2, a natural log of both sides, so that just brings that down to 5,700 k. And then we can solve for k. So a natural log of 1/2 divided by 5,700 gives us a k of, right here, natural log of 1/2 gives us a k of a very small number because it's in scientific notation. So we actually write it as a negative and then 0.001216. That's A. So our actual equation is A of t equals A sub 0 equal to negative 0.001216t. And then B says, calculate the time t for carbon-14 to decay to 1/3. So we want this ratio to be 1/3. So we're saying 1/3 equals e to the negative 0.001216t. So we're going to take the natural log of both sides. So the natural log of 1/3 equals negative 0.001216t. And when we divide by this negative number, we find out that t is, so we're going to take the natural log of 1/3 and then divide by negative 0.001216. Right there it is, sorry. 9,034 years. It's going to take a while. That's crazy, isn't it? 9,034 years. Okay, let's look at 23. So 23 says population growth of the United States is expected to grow from 282 million in the year 2000 to 335 million in 2020. And we're there, we're over that. But I don't know when this book was written, but we're at like 350 million. So it says find a function of the form C equal to the KT that models the population growth for the US. Here, T is the number of years since 2000 and PT is in millions. Assume the trend in part A continues, and what year will the population of the US be 350 million? So this is a good one, we can check this. Okay, so we went from 282 to 335, and that was in 20 years is expected. So we're saying it's expected. Okay, so we're looking to create a function that models this here. So C is our base population of 282. And we're saying that was over 20 years. If it really does grow from this, and it actually grew bigger than that, 335 million. So let's find that ratio, 335 divided by 282 is 1.1879. So 1.1879 equals e to the 20k. So we take the natural log of that. And divide by 20. So let's take the natural log of 1.1879 and divide by 20. We get 0.0086 is our K for 23. .0086. Okay, so our equation is P of T equals 282e to the 0.0086 T. And then they asked us to find out when this would equal 350 million. So we could actually put this in decimals. See, that kind of is fun too. But we could set this equal to 350 into 82e to the 0.0086t. So let's save some room and do this on our calculator. We're going to 350 divided by 282. So that's a ratio. And we're going to take the natural log of that previous answer. And we're going to divide by, because after we take the natural log of the sides, we're going to divide by 0.0086 to find T. So it looks like in 25 years. So 25.11 years. So they're saying that would be the year 2045, but actually we are already there. So they underestimated that growth, didn't they? Wow. So logistic growth is another cool function to look at. And in the lesson, they talk about logistic growth. And it's used for, logistic modeling is used for like populations of animals. It's also used for, they use it also like when we have a pandemic. So I'm sure they use logistic modeling as well for the pandemic. Logistic modeling here is what our modeling looks like. And I'd like to go over what the values mean here. So if you look on the graph on page 384, our function, a logistic model, means you kind of start somewhere and then there's very quick growth and then it planes off. And that's what the population growth, sometimes they use models like that to look at population growth of humans, but also of certain animals. And they want us to do that number 27. So 27 says the population of white-tailed deer in a wildlife refuge 10 months after their introduction into the refuge can be modeled by this. How many deer were initially introduced into the refuge? And then how many deer will be in the wildlife refuge 10 months after introduction? Where T is in months. So there were 300 introduced, and then we're going to see how many are there in 10 months. Okay, so 27 was how many were introduced at the beginning. So let's just look at the, I said 300, I misspoke here. So let's look at N of T. 300 is our threshold. 1 plus 14e to the negative 0.05 t. Okay. So initially introduced would be our y-intercept. So that's what we really want to find is our y-intercept. So n of 0. So let's put this into Desmos and check it out here. So we're going to say y equals, and then 300 divided by 1 plus 14. We're going to put in x for t. So that's an e to the exponent, and that's going to be in the parentheses, a negative 0.05x. Okay. And then I'm going to make a table so that I can adjust my graph. And that's not what I want to look like. This is what I really want to look at. Okay. Let's zoom out a little bit more for you. Okay, there. I just can't get to zoom out much. Okay. So it's saying, what is our y-intercept? So I'm going to zoom in just a little. Click on the graph here. I can see that my y-intercept is at 0 and 20. So our initial population was 20. And then they asked after they asked how many deer will be in the wildlife refuge after 10 months. So we can just put in 10 months into Desmos here and find out that there's approximately 32. It's pretty cool that Desmos does that for us. And I'm expecting you to use Desmos for these, don't worry. Okay. And I wanted to look at one other problem, number 31. Oh. So this one, we're going to do some modeling in Desmos. So number 31, you're going to look at Desmos. We're going to put this data in. So it says, the following table gives the salaries in billions of current dollars at restaurants in the US. Make a scatter plot of the data and find an exponential function of the form that best fits this data. Let X be the number of years since 1970. So that means for 1970 is going to be our base year. So what we're actually putting in for X1 in Desmos is going to be 0. And then 1985 would be 15 years because it's 15 years after 1970. And then this would be 25. And then this would be 35. And 2013 would be 43. And then it says, why must A be greater than 1? Okay, so we'll answer some questions here as we go. So let's go to Desmos and put our data in. We'll turn this one off, and I will save this for you all. And then let's go make a data table. And X1, like I said, is going to be 0, 15, 25, 35, and 43. And then we're going to put in 42.8, 173.7, 25, 7, and 660.5. Okay. And we're going to go ahead and hit our magnifying glass so we can see our data. And it does look like it's exponential. And then to do exponential modeling, you're going to type in y instead of y equals, because you want it to model this. You're going to say a tilde sign, which is up to the left of your number 1 key. So shift and the tilde sign. You can also find it in your keyboard. If you go to your keyboard and click with the A keyboard, your tilde symbol is right here where my mouse is. That's what you're looking for on your keyboard, right there where my mouse is. So I'm going to do A times B. Now, we could make this like what they want. So they want C times A. So let's call our C and our A. So C times A to the X. They want, that's our model. Oh, you know why we have to tell it where. So it's going to be Y1, and we've done this for a while, and X1. So it's going to use the data from Y1 and X1 because that's what's in our table. If you had X2 and Y2, then that's what you would have to reference. Make sure you also click on the log mode box. And this is a pretty good fit because this R squared tells us that it's a good fit. I kind of like to look at that. We don't spend much time on that in this class to use the R squared, but so our parameters are C and A. So I'm going to write it on my paper and I'll show you what it'll look like. So for us, it's going to be f of x is equal to 53.3664 times 1.0645 to the x. So 1.0645 is my multiplier. So I'm just going to make a note here for you. 1.0645 is my multiplier. And then if you take 1.0645 and subtract 1, we get 0.0645. So our growth rate is 6.45%. That's what that tells us. When you take your multiplier, your growth factor is let's just write this. This is really growth factor in technical terms. And then if you take your growth factor and subtract 1, you get your growth rate in percent form. So that's pretty cool. So let's just go back and share that with you. So this would be my starting number of in billions of restaurant sales, right? And then the growing so restaurant sales in the US are increasing by 6.45% per year. Because that's what that growth rate gives you. So let's just write our growth factor, kind of an overall thing that we learned hopefully in this chapter. Our growth factor is the base on your exponent. So that is our 1.0645. And if you take your growth factor and subtract 1, you get your growth rate. And so that's the 1.0645 minus 1 is 0.0645, which is 6.45% increase. And I probably answered other questions that they didn't ask and some that they did. So why must A be greater than 1 in your model? Well, that's because it's a growth. So A has to be greater than 1. Letter C says, from this model, what is the projected sales for restaurants in the year 2015? So that's letter C. So in 2015 would be T equal to 2015 minus 1970. So that would be T equal to year 45. So let's just, T is year 45. So let's just go to Desmos and check it out. So we can actually just go to our graph and grab year 45, and it's a slider. If you grab your graph, it's super cool. It just slides. So you can slide to get to 45. It's one way you can do it. The other way that's exact is if you just go to a new line in Desmos and say y equals 45. Go to x equals 45. It will make a line there, and then you can just click on the dot, and it tells you that sales would be about 888 million. $888 million in sales. And then D says, do you think that it is realistic for this model to be accurate over the long term? So I don't, because exponential means that it just keeps growing by more and more and more and more all the time. And I think it's probably a little bit more like a logistic curve where it's going to have rapid increase and then probably more like taper off a little bit. But it always depends on the economy and what's going on. So no one could predict that we were going to have a pandemic, right? And so that's definitely tapered off on sales for a lot of industries. So that concludes chapter 4, and catch me back for chapter 5.